Hi, everyone. So we're back in Chapter 7 here. We're going to talk about Lagrange's theorem. We're going to prove it. So last time, with much difficulty, we went over some properties of cosets. So let me remind you what a coset is. Coset is a set H, where H is a subgroup. Okay, those are left cosets. HA would be the right cosets. There's a bunch of properties of them, that comes from this symbol. An element A from G is in its own coset represented by itself. Since H is a subgroup, it contains the identity, so A times E is equal to A. That must be in AH. And there's this bit here that says, okay, two cosets are equal or they are disjoint. And also, they all have the same number of elements. Okay? Using these facts, we can show Lagrange's theorem, which is if G is a finite group and H is a subgroup, then the order of the subgroup divides the order of the group. And moreover, the number of distinct left cosets is also a divisor of the group. It's called the index, but it's this formula here. So the point is, all right, so let's assume that A1H, A2H, A3H up to AKH are all distinct cosets, are all of the distinct cosets of the subgroup H. Okay. Since for any A is always in AH for any A in G, this implies that G is equal to the union of all cosets, right? Which means if I take, these are all the cosets, every element of G must live inside some coset, okay? This means that G is the union of the i's of these distinct cosets, right? And not only that, furthermore, two cosets are either equal or they are totally disjoint. So this means, so these two things mean that the cosets of H do what's called partition the elements of G. Okay. Indeed, in particular, this means that the order of G is equal to the sum of the orders of the cosets. But those are all equal, right? okay, to each other by property, what was it, 6. Okay, so that means that the order of k, which is the number of cosets, divides the order of G. But not only that, right? A J H is equal to H for some J, right? Since E H is a coset of H. So this means that the order of H must divide, K times the order of H is equal to the order of G. Since it's going to be equal to the order of A1, H. And that gives us the whole theorem, right? So K is G over H, right? That's from star. This is the number of cosets. That's the formula. And order of H must divide the order of G, since it's a factor of the order of G, right? Also by star. All right. On the other hand, this is really important. The converse of Lagrange's theorem is not true. Okay, there are groups in which the order of a factor of the order of G does not necessarily mean that there is a subgroup with that order. There are some that this is true, right? But let me give you some real quick examples here of Lagrange's theorem so you can see, right? Right, so say I've got Z sub 20, right? And then this is generated by, or this is, right, the integers modulo 20. 0, 1, 2, up to 19. Okay. A divisor of 20 would be, say, 5. Okay. Cyclic groups, right? We've seen this before. Any divisor of the order of the group will have a subgroup of that order, and specific exactly one. We saw this when we did that tree looking thing with the subgroups. So let's say, I don't know, the subgroup generator of 5 would be 0, 5, 10, 15, right? The order of that is 4. That's a divisor. The order divisor of the order of the group, which is 20, right? Indeed, the number of distinct cosets of H here would be equal to 20 divided by the order of the group, 4, which is a coincidence, but maybe not. 5, right? But in general, this is not true. We will see later a alternating group on 4 letters. A4 does not have a subgroup, doesn't have a subgroup of order 6, even though the order of this, the order of A4 is 4 factorial divided by 2, which is 12. No. 4 times 5. Let's say 4 times 3 times 2. Yeah, 12. I was right. Okay. So it's not true. If a group is it does satisfy the converse of Lagrange's theorem, we call it CLT. Or converse of Lagrange's theorem. I know it's not a clever name, but that is. All right. So I've said this before. The index of a subgroup is denoted by this symbol here. It is the number of distinct left cosets or right cosets. We could be doing this all from the right as well. So we could find the index of this guy, and we could, try to find all the cosets of H, but that would be horrific. So instead, we're going to use Lagrange's theorem. I remember how much time we spent last video just trying to find the cosets of these two these subgroups of D4. It could take forever. You'd have to, calculate essentially that number, whatever the group order is, number of elements, that number of sets, and then compare them and, simplify them. It's crazy. But if all you want to do is just find the number of cosets, that's easy. Lagrange's theorem says that the index is n factorial divided by 2. Right? Since that's the order of symmetric group on n letters, n factorial, and that's the order of subgroup. Okay. What about the alternating group? This is index 2, right? The alternating group, remember, are all the even partitions, or even permutations. There are half even and odd permutations. So, number of distinct left cosets of AN here would be 2. You're either in AN or you're not, right? Think of it this way. And maybe this is obvious. So say you have there's an element of Sn, right? Okay. And there's another element of Sn. These are the cosets. right? So everything in here is an even permutation. So you take an even permutation times an even permutation, it's still even. Here, this is a transposition times an even permutation. So it's odd times even is going to be odd. Okay, so those are the cosets. And so the corollary to Lagrange's theorem that's pretty interesting is and important is that the order of an element must divide the order of the group. Okay, this is because you can take the element, right, and find a subgroup generated by that element, a cyclic subgroup. With the order of A is equal to the order of H. And since the order of any subgroup must divide the order of the group, that shows that much there. This also shows that if a group is a prime, has prime order, then it must be cyclic. In other words, there's only one isomorphism class of groups with prime order, because those are the we showed a cyclic group of order p is isomorphic to the integers modulo p. So why is this the case? Well, you know, let A be an element of G with A is not the identity. Okay, then that means the order of A must divide P, and the order of A is not equal to 1. That means the order of A is equal to P, right? P's a prime, so it only has two divisors, itself and 1. That means that G must, order of G must be the same as the order of the cyclic subgroup generated by A. That means that G must be that cyclic subgroup. Okay. Last corollary I'm going to talk about here before we take another little break is Fermat's little theorem. You may have heard of Fermat's last theorem, and well, no, actually, I'll do one more example after this. But Fermat's last theorem was a famous problem that got solved, I don't know, about 20 years ago now. But it was, there's a whole, look it up on Google, Fermat's last theorem, and Andrew Wiles who proved it. It's an interesting story. I'll leave you to that. If you want to know more about it, you can find me in office hours and I'll tell you. But this is another theorem by Fermat, and this is basically a special case of the fact. It's a special case of the fact that so the order of an element, right, must divide the order of G. So that means that A to the order of G must equal the identity, right? So this means that the order of G is equal to the order of A times the index of the subgroup generated by A. Okay, and so this means that A to the order of G is equal to A to the order of A times this index thing. And so that's got to be the identity. So now, why does that help us? Okay, well, let's let G be the unitary group for P. That is, it's the multiplicative group of integers modulo P, right? This is, of course, because P is a prime. So the unitary group of a prime has size P minus 1. And so this means that if there are two cases, right? So yeah, let me say. All right. This means there are two cases. Case 1, A does not, P does not divide A. That means that A is congruent to, well, A is an element, I should say. Yeah. A is congruent to something in the unitary group, right? Which means that A to the P minus 1 is equal to K to the P minus 1, which is 1 mod P. And that's what we need, right? Then multiply everything by A again. You get what you need. All right, case 2, if P divides A, then that means that A to the P is congruent to 0 mod P, but A was already congruent to 0 mod P. So that still works. Okay. Groups that do satisfy the Lagrange's last theorem, Lagrange's theorem, are called CLT, and some examples are perhaps no, maybe you need to investigate this. DN. Okay, I think maybe if you wanted to do that think about if that's true or try to prove that, or disprove it maybe. You could do that for extra credit. We know that cyclic groups, those are CLT. Let's see, things that aren't. for example, A4 is not. There's also another thing. So here, this is an aside. I'm not going to ask you anything about this after this. Groups called solvable. So a solvable group is one in which if there is a chain of subgroups that satisfy the following sort of relationship. The trivial group, and then this is a symbol we're going to learn later, has to do with normal. So not just subset, but these are normal subgroups that are included in one another. H1, H2, this is another distinction we need to write. And then HR is the group itself, such that if you take a bigger subgroup and look at this symbol here, this means this is the group of cosets. So you can take the set of cosets, and if a subgroup is normal, then the set of cosets, together with whatever the operation is that we're going to use, the multiplication that we're going to use for this, turns out to be a group, then that's what makes the subgroup normal. So this symbol here is just the group of cosets. It's like a division. Is always abelian. Okay, for every I, right? Then you have a solvable group. Okay, those are CLT. This is really not really necessary yet, but if you want to read on about those things, you can. Certainly, since A4 is not CLT, then neither is Sn for n bigger than or equal to 4, since A4 is a subgroup of Sn. Sn will not contain a subgroup of order 6 in that same way. All right, so maybe I can finish up this one thing and then actually let's stop here, and I will do this example and another couple things in a third video. Okay, so next time I'm going to show you why the alternating group does not contain any subgroup of order 6, and also finish off the section by talking about what are called orbits and stabilizers and the orbit stabilizer theorem. It's a big section of the textbook, so I'm breaking this up into 3 videos. I hope that doesn't screw you up too much, but we're going to do a couple more examples in the next video. Okay, thanks a lot. Bye.